Hello. We're starting a new chapter today. It's going to be on quadrilaterals. Those are four-sided polygons. You remember what polygons are. Those are two-dimensional shapes created with intersecting straight lines. The blue lines here form a hexagon. I inscribed this hexagon inside of a circle because I want you to see that from the center of the hexagon to any vertex is the same distance. It's the radius of the circle. So each one of these lines has the same length. This is also a regular hexagon, which means that each of these sides has the same length. So I guess I can put my little hash marks in there like that. Now, I don't mean to say that these sides have the same length as these radii. They don't. Well, they may not. It's possible, I think, maybe to create one that does, but that's not really relevant right now. What matters is that it's easy to see that each of these are not only similar, but in fact congruent triangles. There's also something else we can observe. As we go all the way around here, or around the outside here, doesn't matter, 360 degrees. There are 360 degrees in a circle. So if we go, this is one part of 360, this is another part. Each of these are going to be fractions of 360. Well, they're all congruent, so they're all going to be the same fraction of 360. And how many of these do we have? These little, what do I want to call these? Vertices that are created by the radii. I'd like to call them interior angles, but I can't, because the interior angles are the angles formed by the sides of the polygons. We got to call these something else. They're the angles formed by the radii, which go from the center of the hexagon to each vertex. These angles, well, let's see here, there's 1, 2, 3, 4, 5, 6 of them, and they're all congruent, so we just have to divide 360 by 6. And that gives us 60 degrees for these angles here. Each of these is 60 degrees. That doesn't tell us what these are. It just tells us that this is 60. But it tells us something about what these are, doesn't it? Because the angles have to add up to 120. Pardon me. The angles add up to 180. And 180 minus 60 is 120. So these two angles would have to add up to 120. And if we cut that in half, we get 60. Well, as I said, these don't have to be equilateral triangles, but it turns out they are, because we have 60 degrees for all. Well, what about this triangle here? It's going to be exactly the same. These are all congruent, so this is 60 degrees also. Well, these two angles together make up the total angle of this side with this side. The angle formed when these two sides meet is 120. And we have 6 of those. So the total of the angle measure all the way around in this hexagon, remember, not these angles. These angles in the center here always have to be 360. But the angles out here, they can change quite a bit. They don't have to be anything in particular. They depend entirely on how many sides we have. And I think as you fool around, you'll get to see that the larger the number of sides, the larger the interior angle gets, or becomes. So what would the sum of the interior angles of this thing be? Well, 6 times 120. Put it over here. that's what, 720? That's the sum of the interior measures for the hexagon. Now, if we had, suppose we had a pentagon. These angles, as we go all the way around here from the center of the pentagon, have to add up to 360. And what I've drawn here is a regular pentagon. So all these sides are congruent. Each of these radii, or lines from the center of the pentagon to a vertex, they're all of equal length. Which means these are at least isosceles triangles. And what would the measure of these be? Well, let's see here, 1, 2, 3, 4. We've got 5, and it has to add up to 360. So for this one, we just take 360 and divide it by 5. I think that's 72, isn't it? I hope so. That means this angle here is, let's put it right here, 72 degrees. Well, that's not a 2. Gee whiz. 72 degrees. Well, these two angles have to add up to 180 minus 72, which is 108. Divided by 2 is 54. But remember, these 54-degree angles are only half of the angle. We know it's half because these triangles are congruent. Whatever this is, that's also what these two angles have to be congruent, which means this interior angle here would be 108 degrees. For the hexagon, it was 120. For the pentagon, this angle is 108. Well, for one thing, are you starting to see a pattern on what the interior angle would be? If you draw your radii, you're always going to end up, in the case of 6 sides, you'll get 6 triangles. In the case of 5 sides, you'll have 5 triangles. If this were a 4-sided figure, from the center out to the vertices would produce 4 triangles. In each case, you would divide 360 by the number of triangles you had. That would give you this angle here. Now, if you subtract this angle from 180, you get double this angle, but the fact is the interior angle is double this angle. In other words, you subtract 72 from 180 and divide that by 2 to get your 54 here for the correct angle. But what if you don't divide it by 2? Because the situation is such that when you subtract 72 from 180, you get the sum of these two angles, which are equal. The problem is, the interior angle is also double this angle, which is the same as saying the sum of this angle with itself, which means that once you have subtracted this angle from 180, you're done. I went ahead and computed the angles for these triangles that we created, so you can see how we're getting at it. But the fact is, you don't actually even need to compute these angles. Once you see how it works, these two angles are always going to be half of what's left over. On the other hand, they're always going to be half of the interior angle. So all you need is what's left over when you subtract this from 72. In this case, it was 108 when you subtract, when you subtract 180 from 72. In this case, it was 108. Over here, we subtracted 60 from 180 and got 120, and that is in fact the interior angle. And that'll work for anything. If you had 4 sides, then each, we'd have 4 triangles. We divide up these angles equally. They're 90 degrees. Well, 180 minus 90 is 90. which means that the interior angle for the quadrilateral must be 90 degrees. Now if you want the total, that's pretty easy. For the hexagon, it was 6 times the interior angle, 720. For a pentagon, it's going to be 5 times the interior angle, which is 540. And when you get to the quadrilateral, the interior angle is 90 degrees, and you multiply it by 4 and get 360. But can we say more here? Is there some kind of a pattern to this? And we take a look at a couple more polygons here. And this is where I wrote sum of the angles for the hexagon is 720. The sum for the pentagon is 540. For the quadrilateral it's 360. And for a triangle, we definitely know that it's 180. And for the quadrilateral, how do we know it's 360? Well, each of these angles is 360 divided by 4. That's 90. 180 minus 90 is 90. So each of these interior angles must be 90. And 4 times 90 is 360. And this, well, we already know. The sum of the angles in a triangle is 180. We've known that for a long time. So let's make a little table and see what all this tells us, if anything. For 3 sides, the sum is 180. 4 sides, the sum is 360. 5 sides, and you can see what's going on here. Every time I add a side, I add 180 degrees. Starting with 180 for 3 sides. So suppose it's almost like we were taking the number of sides times 180 to get the sum. The problem is we're starting at 3 and not 1. But we can shift that. So if this is, show the dots down to n, what is this over here? Well, I would say that it's probably n minus 2 times 180. See up here, this is like 1 times 180. This is like 2 times 180. This is the same as 3 times 180. And it keeps going up as one more multiple of 180, starting up here at 3. So if we subtract 2, then we get 1 times 180, 2 times 180, 3 times 180, and on down the line. So this is in fact your rule for the sum of the angle measures inside of a concave polygon. Doggone it, I knew I'd say that wrong. It's a convex polygon. What the heck is a convex polygon? Well, the easy way to think of it, the definition has to do with, well, maybe I should just draw one. Well, here's a concave polygon. The actual definition says that with a convex polygon, none of the sides, or the segments forming the sides, are in the interior of the polygon. Yeah, it's a good definition. But functionally, when you're trying to figure out whether it's concave or convex, well, I think the easiest way to remember concave is that if it's concave, it kind of looks like you took a regular one, like this is the pentagon here. Suppose you take a regular pentagon and give it a good kick along here somewhere, so that you cave in part of the side. Well, hence the name concave. Give it a good kick, and you've smashed in the side so it ends up looking like this, and not like the regular pentagon. You could do that, but The trick is you have to, I guess you don't. I mean, if you were like to kick this in, then it would bend in like this. And this side wouldn't be there anymore, it would be like that. That would be concave. You've caved in that side. The other way to look at it is that one of the angles is obtuse. Is that right? No, that's not even right. Forget that. There are lots of pentagons with obtuse angles, so that won't do you any good. I just think of it as, when you see something that looks like it got one side caved in, that's concave. You can analyze the definition, of course, and the definition's in your book. But for practical purposes, when you're taking a test or you want to quickly know what it is you're dealing with, just take a look and see whether it looks like somebody gave it a good kick and caved in one side or not, or one corner. Like over here, I actually kicked the corner and the corner caved in. You could do it this way and produce two more sides. What used to be a quadrilateral is now a very irregular pentagon. This one side has been turned into two sides, which were smashed in. That's the way I look at it, and I hope that'll help you spot them quickly on tests. Just think of giving it a good kick and caving in it, then it's concave. And this formula right here, that's the important thing. We'll use this a lot in working problems in this section. Now, the special case for this is four sides, because, well, the title of this chapter is quadrilaterals. So I've got a feeling we're going to look at a lot of quadrilaterals. And they're telling you right up front that rather than, this formula you should know, but for quadrilaterals you probably shouldn't have to work out the formula. Triangles and quadrilaterals you should just instantly know. It's like a database. You can record data and then retrieve it from the table, or you can have an equation which works it out every single time you want the information. Your brain works both ways. Use equations for numbers bigger than 4. If you've got 23 sides, use the equation to figure out what the sum of the interior angles would be. On the other hand, if you've only got 3 or 4, go to the table in your head and just pull the number out. You shouldn't need an equation for these first two. Now, just like with triangles earlier in the course, we had interior and exterior angles. For this pentagon, the interior angle would be this right here. It spans right across the radius we drew. Well, sorry, that was kind of dumb. I noticed I had written sum next to the 108. The interior angles are h108. The sum is the 540 up here. Sorry. Now, let's get back to exterior angles. Just like with the triangles, if we extend these lines, and we extend them the same way, we could have gone the other direction. For instance, we could have extended this line this way, and then this line this way, but don't do both. If you extend this line this way, and then this line this way, well, you're going to get two sets of exterior angles. You got this one and this one. That's not what we're talking about. When we come up with a sum for exterior angles, we don't mean this one and this one. We got to pick a direction. We can either go this way and extend the lines, or we can go the other way and extend the lines that way, but not both. And to see what the exterior angle should be, that can't be too hard. After all, if we extend this, we still just have a straight line, or a straight line segment. Maybe I should put arrows on these to show that we've just extended the segments now into lines. And they're creating angles here and here, exterior angles. This whole thing is 180. So, what's this? 180 minus 108, because 108's in here. So that's 72. Wait a minute. We got a 72 over here. why did this turn out to be the same as this? Well, how did we arrive at this interior angle? We took this angle here and subtracted it from 180. And that's what we do for every single polygon. We take this angle, subtract it from 180 to get this interior angle. Take this angle, subtract it from 180. Take this angle and subtract it from 180. These angles here that are formed by the radii, we subtract them from 180 to get this angle here. Well, now that we've got this angle here, we subtract this angle from 180 to get the exterior angle. Well, it looks to me like we did something like, if we write this out, in order to get one interior angle, we subtracted this from 180. So let's call this alpha. Alpha would be 72 in this case. It's 60 over here, 90, 120. Alpha is the angle formed by these lines from the center of the polygon to the vertex. However, once we have this angle, how do we get this exterior angle? We have to subtract it from 180. Well, we have 180 minus 180 minus alpha. So our exterior angle is exactly the same as the angle that we'll call them radii. This isn't really a circle, but we could inscribe it in a circle, just like we did over here, in which case this would be a radius for the circle, which touched right here. So why would these exterior angles add up to 360? Well, the exterior angle is congruent to this angle made by these two radii. And there are exactly as many, there are the same number of vertices as there are sides. We have 5 vertices and 5 sides. Having 5 sides produces 5 of these radius created angles. On the other hand, having 5 angles here, well, the 5 sides create the 5 exterior angles. Since this has to add up to 360, these must also add up to 360. The exterior angle is congruent to this angle. There are 5 of these, and that's the reason it's 72 degrees, because we just took 360 and divided by 5. Well, now we multiply that number by 5. 360 divided by 5, multiplied by 5, and what do we get? We get 360. And that's going to happen every time here. Let's take a look at this. The exterior angle is 60 degrees, and we have 6 of them. So that's 360 degrees. Here, the exterior angle is 90 degrees, and we have 4 of them. So these formulas actually make sense. So what we have, the sum of the exterior angles for any polygon is 360. The sum of the interior angles is n minus 2 times 180. Well, let's work some problems. Let's see how this stuff all works out. This section's really pretty easy, as long as you just keep in mind those formulas that we've got here. We used to have, oops, let me write those down again. There's a formula, n minus 2 times 180. That's the sum of the interior angles of a polygon. Now we have a student here who, well, it couldn't be a student. A student wouldn't make a mistake like that. Got a couple of politicians in my state, governor and an attorney general. They're named Inseam and Fleabite. Let's say that Inseam and Fleabite decided to study geometry, and they think that the measures of the exterior angles of an octagon is greater than the sum of the measures of the exterior angles of a hexagon. And the reason, of course, is obvious. The octagon has more sides than the hexagon. What's wrong with what he's thinking? Well, I think we still have that drawing up here that we just looked at. It showed exactly what's wrong with the way he's looking at things. As you add sides, these angles get smaller, which means that the exterior angles get smaller because these angles are congruent to the exterior angles. As they get smaller, these get smaller. So you increase the number of sides, but you decrease the size of the angle. And in fact, you do them at exactly the same rate. So you may go from 72 here to 60 here, but you multiply this by 5 and you multiply this by 6, and you get 360 either way. So it turns out that the product of the two, suppose the number of angles was x and the size was y, it turns out that the product is always 360. The interior angle times the number of angles. So, and what happens, the reason that this number never changes is that every time this number, say, doubles, this number gets cut in half. If you multiply this by 1.2, you divide this by 1.2. And the product always turns out to be the same. It's 360. So, the real problem with the way he's looking at this is that the sum of the exterior angles is independent of the size of your polygon. It's always 360. Doesn't matter what polygon you're looking at. Yeah, here we go. Measures of the interior angles of a quadrilateral. And what do they add up to? Well, we know. They add up to 360 degrees. And here we're given the measures in terms of x. So we have 4x plus 3x is 7, plus 2 is 9, plus 1 is 10. So we have that 10x equals 360. Now the largest angle, first we should figure out what x is. That looks like it's pretty easy. It's going to be 36, right? Now, assuming these numbers aren't negative, 4x dot is going to be the largest interior angle, no matter what x turns out to be, so long as it's greater than 0. And what's 4 times 36? 120 plus 24 is 144, I think. Yeah, my calculator agrees. It's 144. The important part of this was just remembering that the sum of the interior angles for a quadrilateral is 360. Add them all up, solve for x, and then multiply by 4 to get your largest angle. Yeah, here's one. We're going back to chapter or two ago. We talked about similar polygons. Mostly we discussed similar triangles, but similarity applies to polygons of any size. And we're told that we have two similar polygons, and we, in a sense, have the similarity factor here. ST is 6, that's this one here. KL, that's this here, is 10. And this diagonal, I think we're giving us, is 12. Well, the ratio of this diagonal to this diagonal is the same as the ratio of this side to this side. So we just have to write that 6 over 10 equals 12 over, what's that? Or, yeah, I probably should make that like an x. Makes more sense. 6x equals 120, or x equals 20. Or you could have just spotted the fact that 12 is 2 times 6, So multiply 10 by 2 and you put 20 down here, and the ratios will be equivalent. But all you need to do is spot the fact, recognize the fact that diagonals follow the same scale as the polygons with respect to similarity. And there's another one that's, as long as we got these two pictures up here, there's another problem where they ask you to show that any two regular polygons of the same size, such as any two regular hexagons, any two regular pentagons, have to be similar. And that's really pretty easy to show. Just take let's take these two regular polygons. Let's consider the ratio of RS to JK. Let's pretend we don't know what it is. But RS has a length and JK has a length, which means RS and JK are both rational numbers. So we can always take their ratio. It's equal to some number here, K. Or that means that RS is K times JK. Well, okay. That tells us the ratio between this side and this side. That doesn't tell us that that ratio applies to all the sides. Or does it? In a regular polygon, every side is the same size. So RW is the same as WV and on down the line. So I could substitute any one of these into any one of these. And more importantly, I can substitute the corresponding parts. For instance, I can put RW on this side because RW is congruent to RS. And K is just K, it always is. And what's congruent to JK? Well, every side here is congruent to JK, but for our purposes, what's important is that KL is equal to, or KL is congruent to JK. We can stick it in here. That means the lengths are equal. Now through substitution, we have the same similarity factor, which applied to RS and JK, applies to RW and KL. And obviously, we can go around the hexagon or any other polygon, apply exactly the same substitution, and end up with the same similarity factor for every single side, which means they're similar. And if you think about it, it's kind of intuitively obvious, because if every side is equal, one side has to be a multiple of another side. That's always true, no matter whether you have regular polygons or not. You can always pick two sides and write this equation. The question of similarity is, will that ratio apply to all of the corresponding sides on the two figures? And in the case of a regular polygon, the answer is yes. If you just picked any old, say, hexagons at random, and they're not regular, then no, you can't say that because two sides have a ratio, the other sides must all form the same ratio. That's just not true. But if they're regular, then you can definitely say that. There's always a ratio, because they're rational numbers. It's not possible to have RS over JK undefined unless JK equals 0. And we don't have that. So as long as these are rational numbers, regular polygons will always be similar, so long as they have the same number of sides, of course. Okay, here we have 4 answers from A to D, but this isn't really multiple choice. They want us to spot which one of these, or maybe all, any or all of these, may be possible angle measures for a regular polygon with an interior angle that's given here. Well, let's go back to our drawing. How did we arrive at the size of the interior angle? Well, we took the number of sides, divided 360 by that, and then subtracted that from 180. So, our equation for determining an interior angle is 360 over the number of sides, and we subtract that from 180. And the question is, do any of these numbers work? Who knows? Would it do any good to rewrite this? Yeah, it might. We'll see. This is n times 180 minus 360 all over n. I don't see where this actually helps us much. Maybe we're just going to have to do this the hard, slow way and put numbers in here. Remember, for these large numbers, like 40 degrees, I think that's not going to be possible. How could this ever be 40? For instance, let's try it. Let's set 180 minus 360 over n, and see if there's any n which would give us 40, keeping in mind that n has to be an integer. So there may be some n that will give us 40, but it has to be an integer. So the first thing we can do is subtract 40 from 180 and shift this so that we get 360 over n equals 140. So now we have that n equals, just replace, switch places, and we get 360 over 140. Is that an even number? No. We can drop the tens here, but 36 over 14 is not an integer. I said even number. I meant does it come out even. I didn't mean is it divisible by 2. I shouldn't even use the word even. I should just say, is this an integer? No. So this one I'd have to say that couldn't work. Suppose we do the same thing with 75. Well, we can still follow the same form. If this was 75, we subtract 75 from 180, put it over here, and we would end up with this equation, except that this number here would have to be 180 minus 75. And then we'd have n is 360 over 180 minus 75. In other words, this is the final equation I'm just going to keep using, keeping in mind that this bottom number right here is 180 minus whatever angle we're talking about here. When it was 40, then it was 180 minus 40. Now it's 75. So we've got that n equals 360 over 180 minus 75 is 105. Oops, 105. When we work this out, that's not an integer either. So this won't work. What about this one? 180 minus 171. Wow. Okay. That's going to be over 9. Well, that is an even number. It's going to be a real big polygon. At least I think that's an even number. Let me take a look here. And that gives us that n equals 40, which is an integer. So this is possible. That one's okay. Remember I said that the interior angles get bigger as the number of sides gets bigger. So with a huge interior angle like that, it kind of makes sense that you'd have a whole bunch of sides. And this is our last one here. And what would this be? Well, this one we should block these off here. This is for B. This was for C. And this, of course, was for A. We got A. Well, that's not right. That's D. Obviously, I'm doing them backwards. This is B. Now let's check A. What's 180 minus 165? 15, right? And that probably works. And it does. This one corresponds to a 24-sided figure. Notice how fast they start getting big. We only went up 6 degrees, and yet we went from 24 sides to 40 sides. And that's going to keep happening. As these interior angles get bigger and bigger, get closer and closer to 180, the number of sides is going to get bigger and bigger until it's almost infinite. As you approach 180 here, n will approach infinity. But that's not too important in this class, frankly. But you should remember that the larger the number of sides, the larger will be the interior angle. Well, this one's pretty easy. If you remember our table that we had, remember we had 3 sides was 180, 4 sides was 360, 5 sides was 540, and on down, and it turned out the difference at each point was 180 all the way down. Doesn't matter how many sides you have. As you add one side, you add 180 degrees to the sum of the interior angles. Well, what's 540 over 180? In other words, how many 180s did we add? And that's 3. How many sides did we add? Same thing, 3. We add, every time we add a side, we add 180 degrees to the sum of the interior angles. Conversely, if we added 540 degrees to the sum of the interior angles, we added 3 180s, or 3 sides. If you just remember that little table we had before, it's real easy to figure this one out. But it won't hurt to remember that for the interior angles, every time you add a side, you add 180 degrees, which also comes immediately from our n minus 2 times 180. I mean, here we have n, right? So it's n times, if we work this out, it's n times 180 minus 360. And this is always going to be 360. That doesn't change. What changes is n. Suppose I add 1 to n, so now it's n plus 1 from the original n minus 2 times 180. Well, now I'm going to get n minus 1 times 180, or n times 180 minus 180. Here I subtracted 360. Now I subtract 180, which means if I subtract this one from this one, I get 180. I've added 180 degrees by adding one side here. You could look at it either way. They say we have a polygon, and it's important that it's a regular octagon. Well, the regular part's very important. Actually, the octagon part's important also. These two together allow us to determine each of the interior angles. Now I just drew a small section of an octagon. It should be on a line here, and then a line here, and on down this. I drew 3 of the 8 sides, because that's all we're concerned with. What is the total number? The sum of the angle measure. Remember, that's n minus 2 times 180. In the case of an octagon, it's 6 times 180. That's the total. But we want to know the interior angles, so divide that by 8, because we have 8 of these interior angles, and we have to divide up these degrees amongst the total. So we got 3/4 of 180. Well, if we do this, perform the multiplication, I get 135 degrees for an interior angle. Well, that's fine, because this straight line here means that these two angles are supplementary. That means this angle right here is 180 minus 135, and that's 45. Well, this is a regular octagon, so this angle is the same as this angle, which means this angle has to be the same as this angle. We've got another 45-degree angle here. Well, we got two 45-degree angles. That leaves us with no choice. We got a 90-degree angle here, and I think that's what they asked, isn't it? What's the measure of the angle? Yeah. So, by figuring out the interior angles, we can easily compute the supplement on each, and that gives us the angles in the corner vertex of this triangle out here, created by the intersection of the extension of DC and AB. And they ask, at what angle do these two extensions meet? 90 degrees. Well, this wasn't too tough, just a matter of keeping track and adding things up right. And that's about it for now.